Sånn. Da skal du få noen ting.
Dear ladies and gentlemen, attendees of the inauguration of the BETZY supercomputer, my name is Andrea Gruber, and I was asked by the organizers to present an insight about the use that we at SINTEF Energy Research do of supercomputing, and in which research context this is done, and provide some examples. So this presentation will give just that. So first of all, some acknowledgement. As you see, we collaborate with both the private sector in the gas turbine OEMs and an energy company like Equinor. Of course, there are some institutional partners that provide part of our funding, and also many academic collaborators that I will not list now one by one, but that are shown in the pictures. So first of all, a brief outline of my presentation. I will provide the context about the clean and efficient thermal power cycles, so why we do this research, and then I will provide an overview over the methodology that we use and why we need high performance computing to do that. Then I will also provide some examples of use of supercomputing in this context. And finally, some challenges, future challenges and the outlook. So, air-breathing thermal power cycle. As I say here, they are powering the world today. They go from gas turbines for land-based power generation to reciprocating engines, and to aerogas turbines for travel, for airborne travel. They have in common that they leverage on a working fluid, which is air, utilizing a very small amount of fuel in comparison to the working fluid to produce mechanical work or electric power. So they use the oxygen as an oxidant to enable chemical reaction, but they leverage on the nitrogen, which is available in the air, to achieve huge power scaling. And this is the main advantage of these cycles in respect to electrical and electrochemical conversion, which cannot enjoy this huge scaling. So the main takeaway here is that thermal power cycles are not intrinsically dirty, but as clean as their combustion technology and fuel they utilize. So simpler fuels chemically mean cleaner exhaust, and hydrogen, which we are studying at SINTEF Energy Research, is one of such fuel, very simple and very clean. So the problem in combustion devices is turbine combustion. There is a tyranny of scale, as I call it here, because there is a wide range of scales that have to be considered. Typically, we look in our work at the continuum, which is comprised between the centimeter or meter scale to few micrometers. We don't go further down in this scale, but this already represents a huge challenge. So all the spatial and temporal scales that are spanned here are intrinsically and inherently coupled. Of course, experimental measurements and laboratory experiments can provide some insight about these processes, but they are still limited to few quantities simultaneously. So what experiments still lack today is what we call data completeness. So the knowledge, which in many cases it's badly needed for about multiple quantities at the same spatial location and simultaneously. So this can hardly be achieved by experiment. And this is where the modeling technique that I will discuss today comes to help. Ultimately, industrial applications need expensive experimental verification, validation, and demonstration. But of course, so experiments are always needed, but they are very expensive. And so it's important to limit their use. But for detailed physical insights, we have to look elsewhere. So in the industry, CFD or numerical modeling of turbine combustion processes have been used for decades now. And the most common approach is called Reynolds Averaging, in which the equation of motions are averaged. This is computationally affordable, and it's therefore widely deployable in industry. However, it gives limited accuracy for complex flows that are highly curved, or they have swirl. In the case of swirl, they have also limited accuracy for reactive flows, because especially when you are looking for complex kinetics or emissions. More recently, there has been a wider adoption of large eddy simulation, which resolves all large scales. So these are represented correctly. However, the small scales are modeled in LES. So LES is computationally more expensive. It's still usable in industry, and it is used to a lesser extent compared to RANS, but it's still usable by industrial actors. However, and it's also more accurate for complex flows. However, it still has limited accuracy for reactive flows, because reactive flows are and chemical reaction are rate controlled by the small scales, which in LES are still modeled. So the main takeaway here is that to date, RANS and LES approach have played a peripheral role in industrial R&D in the energy field, at least. Therefore, we have proposed years ago the use of direct numerical simulation in this context. First, a definition. So I use this by Coleman and Sandberg. DNS is a numerical experiment producing a series of non-empirical solutions from first principle for a virtual turbulent flow. As such, DNS provides a complete knowledge unaffected by approximation at all points within the flows, at all times within the simulation period. So, of course, this is very good because it gives both data completeness and very high accuracy. However, the computational domain size must include the largest scales of the flow. So the computational domain has to be as large as the largest scale. And also the grid spacing must resolve the smallest scales. The bottom line here is that this implies that the number of floating point operation required increases at least as the Reynolds number, as an exponential of the Reynolds number of the domain size and of the number of species that I indicate here as NS. So presently, this limits really the Reynolds number of flows that are representable by DNS to approximately 10 to the 4th. The main takeaway here is that high performance computing is needed by DNS and for its deployment to applied energy research. Without high performance computing, DNS will not be usable in this context. So, can DNS be useful in applied research? Well, first of all, I can say that DNS cannot be a brute force approach to device design. So we cannot use it on the design of full geometries and complex geometries. DNS is primarily a powerful tool to obtain scientific understanding and detailed insight. Also, DNS can be used to test turbulent chemistry interaction models, so to test coarser models and to see how good or bad they are, and to complete and complement experimental data. Also, and this is what we have done mostly at SINTEF, DNS can be deployed on small canonical unit problems that have key relevance to industrial devices to gain physical insight. So here in this talk, I will present briefly, very briefly, 3 examples in which DNS has been used in these canonical unit problems that are relevant for application. The main reason why we do this is hydrogen firing of gas turbines that poses important R&D challenges because of the high reactivity of hydrogen. And DNS here provides key insight. So one problem is the fuel injection, so that it's also known as a canonical problem, the jet in cross-flow configuration. Another problem is the flame flashback, in which a premix flame moves away from its stabilization position in an unwanted direction. And also, we have used DNS to examine auto-ignition stabilized flames at reheat condition. I will come back to what this means more in detail. So I have to acknowledge, of course, our collaborators at the Combustion Research Technology Group of Ansaldo Energia, formerly Alstom, in Baden, Switzerland, that were instrumental in the definition of all of this, of most of these DNS cases. So going to the fuel injection problem, we have a typical gas turbine combustor in which the fuel is injected through small nozzles. And the problem is especially for highly reactive fuels as hydrogen. A typical computational cost for a DNS of an injection problem, of a fuel injection problem, as you see here, is approximately 30 million core hours per case. And the DNS has provided key insight about the anchoring mechanism and the role of hydrogen diffusion in facilitating the flame anchoring. So I don't have really the time to go into detail here, but the bottom line is that experiments and coarser CFD modeling could not provide this insight that is key for the development of these injection systems. The next topic is the flame flashback that I show here in an experiment by Noel Clements at UT Austin, in which I show the flame that moves upstream from the stabilization location on the left towards the right. So flashback is a key challenge, especially in flame stabilization for highly reactive fuels as hydrogen. Here we have done DNS calculation of this configuration, and they cost approximately 10 million hours per case, also in this case. And here too, DNS revealed previously unknown features of the flashback mechanism, where I show here in the picture, what I show here in the picture is the flow reversal that happened just upstream of the flame front, which was previously unknown, and that has helped explain how flashback take place, and therefore how this can be mitigated. Finally, I mentioned the auto-ignition control flame stabilization, which is in heavy-duty gas turbine the technique with the best potential for hydrogen firing. Here we have conducted DNS of a hydrogen flame at reheat conditions. So in this specific and very unusual combustion condition. And in this case, we have had to also use a slightly more complicated geometrical description of the combustion system that you see here is implemented through a multi-block grid. This was the most expensive case we have done to date, and it costs about 50 million hours per case. Here, DNS has provided the first known quantification of the combustion mode in this system. So due to the very specific geometry of this combustion system. You have the part of the flame is auto-ignition stabilized and part is propagation stabilized. And for the designer of this system, it's of key importance to have a quantification of how much fuel burns in auto-ignition mode and how much fuel burn in propagation mode. And we have provided that through the use of DNS. So these three cases show the way we have utilized DNS to acquire information and insight that is otherwise not available by any other means. Before concluding, I would like to explain some of the challenges that I see at the horizon here. So first of all, we use what is called Mpi Parallelism in explicit spatial differentiation and temporal integration that has been an enabler to date, no? And in which the domain decomposition is done among the MPI processes, and each MPI processes is handling approximately 20 cube or 50 cube subdomains. So this surface to volume ratio is an important parameter in the optimization and varies case by case. For example, depending on the chemical complexity. The inter-process communication is only between nearest neighbors. And this fact, the fact that you have very limited all-to-all communication makes this approach very efficient in scaling up to higher number of cores, right? So when we will transition from petaflop to exaflop scale, this will allow larger domains and or larger Reynolds number. But there is a problem. And the problem is that if the per core computational speed hits its ceiling, and it already has, the wall time unit cost will remain unchanged. This means that the total affordable integration time of the physical problem will stagnate. And I will show on the next slide that this has already happened, really. So a 1,000-fold increase in supercomputer size also implies that the node failure will happen more frequently and a larger distance in the machine architecture. So there must be in place a robust failure recovery mechanism. This means in practice that we have to migrate sooner or later from an MPI-based framework to from a synchronous MPI framework to an asynchronous data-aware task-based approach, as an example, Legion, and we have already started to do that. This because this will provide improved parallelism, load balancing, and robustness against failure and scheduling flexibility. Also, when looking at DNS of high pressure combustion, for example, or at larger device, larger grids, we will need new methods to do adaptive mesh refinements, which in DNS, it's not state of the art yet. So all of the above basically further separates the application implementation from how the application is mapped to the system resources and executed. And this means that we will need a closer collaboration between the physicists like me and the computer scientists that design these codes. Referring to the stagnation of the integrated physical time, I show here an historical perspective, the increase in the problem computational size, which I denote here by the grid size times the number of species. And you see by the red line that this has increased exponentially from 1995 to today. However, what you see on the right here is that the CPU clock frequency has only increased linearly. So the bottom line is that the increase in problem size has mainly been achieved by massive MPI parallelism. So going from an order of 100 to an order of tens of thousands of cores, right? But the worrying part here is that the integrated physical time has not increased that much. and has in a way stagnated. So the reason for this is because the unit, assuming highly optimized code, the subdomain, the time needed to compute each subdomain has stagnated due to the fact that the CPU core performance has stagnated. So the main takeaway here is that in the future, an increase in CPU and core performance, so a faster execution, is badly needed here. And a transition to GPU-based high performance computing, while it is helpful for point-wise operation, it is not very helpful for spatial derivation. So that will not solve all problems. Finally, my summary and outlook. So direct numerical simulation and high performance computing have enabled unprecedented insight into key physical processes, facilitating development of low carbon technology. Oh, oops, I went the wrong way. So DNS is now a mature fundamental research tool, and early adopters have also supported this into the development, into research and development of applied in combustion equipment. The transition to exascale will automatically allow DNS of at high Reynolds number, larger domains, and more complex chemical kinetics, but not necessarily all of this at the same time. It is clearly recognized also that our algorithmic improvements, for example, Legion and adaptive mesh refinements, are necessary to proceed significantly closer to device size DNS calculation. In general, proper DNS or turbulent reactive multi-phase flows is and will remain elusive. This is due to the complexity of multi-phase and the fact that even the basic models are not easy to represent even at the DNS level. So finally, important limitations have to be expected in performing DNS of slow processes that are characterized by long time scale. And this is due to the integrated timescale limitations that I have referred to. So this was it, and I conclude my presentation now.